Hey chat, this is Sirle. This is just going to be a quick review of moles and concentration of solutions. While watching this video, I highly recommend you have a pen and paper nearby as well as a calculator so you can follow along. Let's start with the concept of a mole. So suppose I have 10 eggs and this is an exact value, there really are 10 eggs. I know that one pair of eggs is 2 eggs. So if I wanted to express my 10 eggs in terms of the amount of pairs, I will have to convert with a conversion factor that's 1 pair is to 2 eggs. The eggs are in the denominator because I want eggs to cancel out and pair to remain. So using this calculation, I now have my new unit of pairs. Specifically, 10 eggs is equivalent to 5 pairs of eggs. How many moles of eggs would that be? So following my logic in the example, that's simply 10 eggs multiplied by the conversion factor. So for every 1 mole, that's 6.022 times 10 to the 23 eggs. Using my scientific calculator, 10 eggs is 1.661 times 10 to the negative 23 moles. Again, it's very important to track that the units cancel out. In this case, they do because the eggs are found both in the numerator and denominator. And I hope this really drives home the idea that mole, just like pair, is a measurement of how much of something there is. In this case, mole describes particles such as ions, atoms, or molecules. But why do we really need to review moles? Moles are helpful because they can help us talk about atoms in terms of grams instead. We can actually see grams, we can actually measure grams. So it's very helpful for us in the laboratory. If we look at a periodic table, the mass of an atom is provided in atomic mass units. But if you consider 1 mole of that atom, it's still the same value in terms of atomic mass units, but instead of atomic mass units, they are now in grams. Very convenient. So what do I mean by this? Let's work out this example. How many moles of oxygen are there in 1.23 grams of carbon dioxide? So we're given with 1.23 grams of carbon dioxide. We need to look at the periodic table and locate the molar masses of carbon and oxygen. We want to find the moles of oxygen, right? We really need to know the mass of carbon dioxide itself. To do that, we need to add the individual masses of its atoms. Carbon dioxide has a molar mass of carbon, 12.01, plus 2 atoms of oxygen, which are 16 grams per mole. And using my calculator, 1 mole of carbon dioxide should be 44.01 grams per mole. This is just a simple conversion problem. We'll start with 1.23 grams of carbon dioxide. We know that in 1 mole of carbon dioxide, 44.01 grams per 1 mole. Again, the grams are in the denominator because I want them to cancel out. We want to look at oxygen specifically. So, I need to convert carbon dioxide into oxygen. We know that in 1 mole of carbon dioxide, there should be 2 moles of oxygen atoms. Again, because it's CO2. If you look at the final unit, it's now moles of oxygen, which is what we were looking for. So plugging this in a calculator, 5.59 times 10 to the negative 2 moles. In this case, I reduced it to 3 significant digits to be consistent with the given, which is 1.23 grams of carbon dioxide. We should now be ready to talk about concentration. As a review, Concentration describes how much of a substance is present per some amount of solution. The most common unit of concentration is molarity. So in this case, molarity describes how many moles of solute there are per liter of solution. That's equivalent as well to millimoles of solute per ml of solution. We signify concentration in terms of molarity in square brackets. For very small values, for example, times 10 to the minus 3 or times 10 to the minus 7, we could use a p function instead to scale up that number and make it something more usable. So when we perform negative log of molarity, we are performing the p function. If you could recall, pH is the negative log of the hydronium ion concentration. We have other units of concentration in terms of mass of the mixture or solution. We have percent, parts per thousand, parts per million, and parts per billion. In each case, it's mass of the solute divided by mass of the solution times some factor. So, for example, if you want a percentage, you multiply it by 100%. If you want it to be expressed in parts per thousand, it's 1,000, parts per million, 1 million or 10 to the 6, and parts per billion, you multiply it by 1 billion or 10 to the 9. There's also a unit of concentration in terms of weight per volume. So that's grams of solute per milliliters of solution. And this is in percent, so we multiply it by 100%. Another value that is important is the density. So the whole solution can be described using the density. So it's not the solute in terms of the solution anymore. It's the grams of solution in terms of the milliliters of solution. Alright? So density is usually expressed in grams per ml. Sometimes it is expressed in kilograms per liter. Those two are equivalent, G per ml and kg per L. It just so happens that you multiplied 1,000 to both the numerator and denominator. So since you're essentially multiplying by 1, they are the same thing. You might encounter something called the specific gravity. That's essentially the same as density, but without the unit. Here's something interesting. If we assume an aqueous solution to have a density of 1 grams per ml, that is the density of water, then look at what happens to parts per thousand. Parts per thousand is gram solute over gram solution. But if I multiply it by the density, which is 1, so this is not illegal, I can actually cancel out gram solution, leaving me with gram solute per milliliter of solution. And by multiplying it with 1,000, which is provided in the formula for parts per thousand, I am actually converting my parts per thousand into a new unit, which is gram solute per liter solution. Using this same logic, parts per million is also milligrams per liter, and parts per billion is also micrograms per liter. Of course, this operates under the assumption that the density of the solution is 1 grams per milliliter. In many cases, that is not true. So, PPT, PPM, and PPB in terms of grams per liter, milligrams per liter, or micrograms per liter are approximations. And for very exact work, you should not use your units in this way.